All right, hey guys, what's going on? So today we're going to be covering the affine connection. All right, again, make sure to hit that like and subscribe button if you like this kind of content, and go onto my Patreon page if you want exclusive and or early content as well. On the Patreon page, I'm hopefully going to be starting a collection. Collections are things you can start on Patreon where you can get summaries, where I'm putting summaries. And these collections are going to be divided by quantum field theory, by general relativity, and these collections are just now starting to grow there. So again, if that's something you're interested in, summaries in advanced science, go ahead, go onto my Patreon page, donate to this channel. Anything you donate is going to go specifically into growing this channel as well. Now, with that being said, let's get right into the topic. Okay, so we're going to be talking about the affine connection today. I just want to make a quick note, really quick, about the course or the trajectory of this playlist. So there's a lot of really good tensor calculus explainers out there on YouTube already. Some of these are good, or this guy, Xylix, I really like his material. Eigen, Chris, Robert Davey, Andrew Dotson, another very famous, very well-known sort of undergraduate physics guy who sort of makes physics funny and understandable as well. And I'm trying to put myself on the map as well, right? I'm someone who is interested in biophysics, but also interested in other areas of advanced science. Hopefully so that I can, when I learn this kind of stuff, I can integrate it into my own research. And I'll be making a biophysics playlist as well. That's going to be coming out hopefully very soon. But the difference here between what I'm going to try to do and what you find on YouTube is that I really want to go deep. I want to start. I'm going to start at the surface, right? I'm starting at the affine connection. I'm starting at the metric tensor. I'm really laying the groundwork. But then, what I want to happen, what I want to have myself distinct from all these other YouTubers, that I want to add more to the content here, right? So more on the biotensor, more on some of these more lesser well-known tensors that are going to be very useful in helping us understand something about differential geometry as well, which is why I have an ongoing differential geometry playlist as well. We're going to go fairly deep into geodesic deviation, spin connections, the ADM formalism, and much more. Okay, so this is what you're going to plan. This is what I'm planning on doing. This is going to be a huge learning experience for me, as well as hopefully a learning experience for you guys. In order to have this knowledge, however, we need to establish a solid foundation. So with that being said, let's get into the affine connection. So what we've talked about before is that we can construct little vector spaces at every point in time. Okay, every point, or not every point in space-time, right? So this manifold is a manifold or a model of space-time, right? So it's four-dimensional manifold. Right here I'm just showing 2 dimensions, but there's 2 that are embedded that we can't really see. And we have this red vector. So this red vector here is an element in a vector space, right? So this vector space, we said was TP, which is a tensor, a tangent space at the point P, right? So here I have X, so this is going to get a little confusing. I'm just going to say this is a tangent space right now, right? And the point X right here, I'll put P. So this is a point P. X is not really the name of the point. P is the name of the point. X is going to be the coordinates of that point. Okay, and then we can construct a vector as a function of the coordinates of that point, like this, right? So these are the coefficients, right? So we can understand this as x0, x. I'll make that chi, right? So chi 0, chi 1, chi 2, and so forth. And these are all functions of the temporal part of the manifold, the x dimension, the y dimension, and the z dimension of the manifold, and so forth. So we have this space, we have this vector space, and suppose we have another vector space over here, And these two vector spaces are divided by this delta x here. Okay, so there's this change. Oops. There's this change in the in the distance on the manifold that we're traveling, and then between the 2 points, say this is point Q. Or if that's point Q, this is going to be our tangent space at point Q. And what we have going on here is here's our vector now. Here's the new vector, x alpha, at some new spacetime coordinate, okay? This is that x plus delta x. The red here is going to be, well, we have a vector here, right? We have a vector here. The vector here is what this vector would be if it was in this vector space, okay? So this is what the parallel means, right? So this vector would be this vector if it was in this parallel space, if it was in this tangent space at Q. And that's why we're calling it parallel, because when two vectors are parallel, that's sort of the concept of sameness, the idea of sameness, right? This is not really a technical term, but if we were to take this vector in this vector space and transpose it over to here, well, the basis might be different. So that means this vector is going to be different from this vector, but it's going to be different in a way such that if we were to bring it back here, it would come back to the same vector. Okay, so we could, if you will, take this vector, back propagate it by some function, say, and we should get this vector back. Okay, so that's what this parallelism or this sameness stands for. Okay, and we'll get into the back propagation functions, push forward and pull back functions later. But really the point here is that we have this vector, these two vectors in this vector space. One is what this vector would be if it was over here, and the other vector is what the vector is evolving into as a function of spacetime. Okay. All right. So we can develop two equations based off of these two identified vectors. So one is for this blue vector, right? So we can Taylor expand this guy, and we get this guy right here. Okay. Upon first approximation. Okay, so this is a Taylor expansion of this vector. And then we're going to define this guy right here. And this here is the difference between this guy here and this guy right here. So the two red objects, or the two red vectors, there's going to be a difference between the two, okay? Because these aren't the same vector spaces. They're not the same vector spaces, and so we say they're the difference between the two. And so this is, again, difference in the components of those vectors. All right, so we have this bar, and this is what's going to, this thing, therefore, is containing all of the elements or all the information regarding what parallelism means in more of a mathematical sense. And we're going to dive deeper into this now. This is what the affine connection is going to tell us, ultimately. And so let's do this. So we take the two equations. We're going to subtract the two equations from each other, and we get this. And then when we subtract the two equations from each other, what we can do is we can divide both sides by delta xb. Right, so delta xb, again, that is this right here. So this is that little green part that we're putting up in here, and the b just refers to, again, it refers to, it's some delta x0, delta x1, delta x2, and however many dimensions a manifold is, in this case 4, that's what those guys are, that's what that b represents. So this is just like a specific way of writing the small change in space-time. Okay, so we're dividing both sides by this, and what we get when we do that is this, right? So we're going to say this side looks awfully like a derivative. So we're going to call this a derivative on this side. Derivative of x alpha. Derivative of x alpha. And so here we have this guy right here. So when we split these two guys out, right? So we're going to have this guy here, and we're going to have, I'll do a different color, plus this guy here. Right, so that's the purple up here, and that's the black. And so we get is this equation, which is what we're going to call the covariant derivative, but we still need to take a look at this because this here we said is going to contain all the mystery in that parallelism, or that sameness, right? Because this bar is what defined that. All right. And so we're going to make a few assumptions here. So we're going to expect that this object is going to be linear in this, which is that small change on the manifold, and in the components of this guy as well, right? So there's no non-linear dependence of this small change when we move in some direction on that manifold. Okay, so this is going to be linear. That's what I just said. It's going to be linear in 16 components, and it's also going to have space-time coordinates, right? So it's going to be linear in this guy. That's what we just said, and then this guy, and then we're going to have space-time components on each one. Okay. So all of these guys, we can compactify all of this into something that looks like this. And this is what we're calling the affine connection, or this is what we're going to be calling the affine connection, or the Christoffel symbol. The reason, again, it's a connection is because we're in some sense connecting vector spaces by means of this small change in x on the it's a vector at p. These two guys are vectors at p, but they're telling us in what direction we're moving on M, the manifold, right? So M, and these two guys tell us what direction, even though they're vectors in this tangent space, right? So these two guys are, you could say they're, I can make this such that we have delta x 0 and delta x 1, say. Even though they're in the vector space, they're telling us the direction on the manifold we're going. And so in that sense, that's why it's called a connection, right? Because we're going to leave that vector space and we're going to enter another vector space. So this object takes in the original vector at that vector space and the displacement and yields, that displacement are these two guys, or these guys. And this displacement yields a vector that represents change from the original vector. Right, so it's gonna yield a vector that represents some change from the original vector. So what does this look like? So we have some distance or some direction. So this thing is going to get fed into our object, and this guy is going to get fed into our object because we need this guy, obviously, and we need a direction that it's going to travel. Those two objects are going to get fed into this object, which again is in P, okay? This is going to be a field also, and we'll see that in a few minutes. But this guy, we can think of this again as a machine, and then we're going to get components, and the components are going to be the components of a new vector in P, right? So this is, again, we'll call this at P, so this is our tangent space at P. these components are going to be the components of a vector at P that represent that change, that change when we travel some distance in this direction. Okay, and so that's what this is telling us. Right? This is that vector, the alpha. So I can put alpha in green, right? Because that's this vector right here. So that is this right here. And these guys are going to give us the components. By default, we're going to make it a negative, and we'll see why. But we're going to put that minus sign there. We'll see why. These are those components, right? So, and then these guys here are going to sum over the components of the original vector and the change in the distance. The vector that represents the direction that we're traveling, essentially. Okay. Okay, so if we clean things up a little bit, here's the picture we're dealing with. So we have our vector space, or our tangent space at P. So this is our point P. So T, P. And say we have our vector. Here's that green vector we were talking about. But what we want to do is we want to feed in this guy. Right, so this guy again is a vector in this space. This guy is in this space. I'm just putting it here because this guy, the vector in this space tells us again the direction we're traveling on M. Right? So this is a manifold M. And what we are doing, what we want to do is we're saying we're feeding in these two vectors and into this machine. This machine is going to spit out 4 components that are going to be the components of this new displacement vector. Okay, and this new displacement vector represents the derivative. It represents the change, the change in this vector as it travels in some small direction. Okay, and that's that. So the change in some vector as it travels in a small direction is going to be a vector. Okay. Again, because it's going to be a vector, because if we go back to this picture, that vector is the difference between these two guys. Okay. So that's that difference. Okay. So we've cleaned things up a bit. We have this picture in our mind now on these sort of machines operating at each point in space-time. Okay. So what we want to do now is we're going to say, well, this is that equation that we've seen before, earlier on in the video. That's this guy right here. Okay. And this here contains all the notion of parallelism. And so what we've said that notion of parallelism is encapsulated in this guy. Okay. And so this is the covariant derivative. This is what we're going to call the covariant derivative. This is the derivative of chi, or big X, in the direction of some vector that has components b to it. Okay. And this is how it's going to be defined. It's the derivative, the derivative of that vector plus some other part. Okay. This other part again tells us the information regarding how the parallel vector, what the parallel vector is like in that during that change from one point to the next. Okay. Right. So again, this part deals with the straight up derivative, how it's changing, and then we're adding to it the sense of parallelism to that derivative. Okay. And we're going to dive more into this later. Right now the aim here is again just to talk about the affine connection. Okay. And in the next video we're going to be talking more about the covariant derivative. So recall that our vector spaces can be endowed with an inner product, and therefore we have an inner product as well, and therefore some special rank 0, 2 tensor, it's going to mimic that inner product. Because remember, inner product takes two vectors, spits out a number. So there is a tensor out there, the metric tensor that we've talked about, that takes in two vectors and spits out a number. So if we take the components of the metric tensor and have them equal to the inner product component, the output of the inner products, the inner product in that space, then we get a special that's a special metric. It's called the metric tensor, and it spits out a number. So the picture here, it's more complex than this, as we know already, right? Because we have tensor spaces, or we have vector spaces that have tensors in them. We have also covariant objects, or we have covector objects as well. But the idea here now is, okay, we're going to investigate the covariant derivative, but we also want to investigate how, if there's a relationship between this space right here, okay, and this space right here. Again, this space is given to us by knowing something about the inner product in this space. So if we know this, we can construct this entire space here, okay? And if we know what direction we're traveling in our manifold here, then we can get another space here. The problem, not the problem, but the next big question is, is there a relationship between this and this right here? And can we calculate that relationship? So we're going to do that. We're also going to investigate the covariant derivative, and we'll do a lot more in the coming videos. So with that being said, I hope you guys enjoy this kind of content. Make sure to hit that like and subscribe button. Make sure to go onto my Patreon page, and I will see you in the next video.